The overall goal of this experimental system is to generate and measure rotation and torque at the nanoscale using circularly polarized optical tweezers. The rotating objects can be interrogated using additional instrumentation for Brownian dynamics analysis and light scattering spectroscopy.
This method can help answer key questions in nanoscale thermal and optical physics, for instance related to nanoparticle Brownian diffusion and transfer of optical angular momentum to a nanoparticle.
The main advantage of this technique is that it allows stable nanoparticle rotation at high frequencies, and that the measurements provide detailed information about the nanoparticle and its immediate environment.
The idea is to trap a metallic nanoparticle by a focused laser beam in an optical tweezer setup. If the trapping laser light is circularly polarized, the nanoparticle will rotate due to transfer of angular momentum from the light. Construct the setup around a suitable inverted microscope. The setup includes elements for both the optical tweezers and measurements on a trapped particle. This is a schematic representation of the setup. For now, focus on the elements for the optical tweezers. Choose a 660 nanometer linearly polarized laser with a stable output power of up to 500 milliwatts. Use lenses in a Keplerian telescope configuration to expand the beam. Use mirrors in kinematic mounts to direct the laser beam to the microscope. Inside the microscope, use a 50-50 beam splitter to couple the laser light into the objective. For alignment and data collection, include a camera in the path of the reflected light. In this case, a pivoting mirror inside the microscope can direct the light to it. Adjust the Keplerian lenses to expand the beam. Make the beam slightly larger than the back.